Hello everyone, welcome to Scholar Lab. Our simulations can transform your teaching approach, making lessons much more interactive and captivating for your students. Scholar Lab is a distinctive virtual laboratory that brings intricate STEM concepts to life through engaging simulations. This tool is crafted to aid students in comprehending and applying scientific principles in practical situations. In this exciting simulation, we are diving deep into the fascinating realm of how metals behave under stress. When you apply a large force to certain metals, they may stretch, compress, or even shear. But can they return to its original shape? Let's explore their elastic behavior and find it out how far you can push these materials before they undergo permanent deformation. Let me open elasticity simulation for you. Each simulation begins with the game plan. This outlines the procedure, observation, learning of the simulation. Our main objective of this simulation is to explore and perform the various experiments and understand the elastic behavior of respective metals under the large amount of force. Let's get started. This simulation having 4 different parts. Under lifting of crane, we are bringing our kids to dockyard to measure tensile strength and stress and shearing stress. Here we have 4 different containers of different weights and the wire which is hanging over here which can be altered. You can choose the wire material from stainless steel, tungsten, aluminium or copper. Let me fix that to tungsten and the radius in millimeter of the wire which can be changed using this slider. Let me fix that to 20 millimeter. After fixing these values, you can click on set values to begin with the experiment. Now I'm going to start with this smaller object or smaller container out of these 4. So I'm clicking on the first container, it lifts up. So delta L value is given over here in the zoom in view. I'm clicking on it again to place that to the another side of the dockyard. Now the question is calculate the delta L. It's 1.15. Either you can click on show answer button or click submit to check your answer. Now you have to calculate the delta Y based on the delta L value. Let me put the delta Y value and clicking on submit. Similarly, you can conduct the experiment with other containers also. Calculating the delta Y using delta L. While taking on the largest container out of these 4, what happens to the wire strength? It can't even take that out. So which indicates the tensile stress or strain on that wire material. By clicking on this table of readings, it will give you the overall reading of the material length, radius, mass, delta L and tensile strength and stress. Let's move on to the next part of lifting with crane. that is shearing stress. Shearing stress, which occurs when a force is applied to twist or slide one part of the material relative to another. Here we have three different containers and the crane material can be chosen out of these four. Let me fix that to tungsten and area of cross section, that is 10 now. You can start with the smaller one and the shearing stress or delta x value is given over here, that is 3.85. Now we have to calculate the delta G value using Young's modulus formula. Similarly, you can do this with other weight as well. By clicking on table of readings, it will show you the material, area, mass, shearing stress and strain and overall delta G value. Let's move on to the next part of the simulation, that is Young's modulus. This experiment allows you to understand how Young's modulus quantifies a metal's resistance to deformation. By applying force to the metal and then removing, you will measure how much the metal stresses or compresses and whether it returns to its original shape or not. Before starting the experiment, let's fix the wire material using this drop down. Let me fix that to aluminium, and the radius you can change using the slider, and the initial length is also can be changed. After changing all those, click on set values and I'm going to load this Young's modulus setup. By clicking on the weight will be added on one side. Can you see the bubble over here? That will give you the vision of where the weight is more. The bubble is balanced now. Let me add one more weight to one side. To balance the bubble, I am clicking on speedometer. The readings is shown over here, that is 0.19. And the effective mass is 1 kilogram now. Now I am using screw gauge to measure the thickness, that is 1.08. Then I am using scale to measure the length of the wire, that is 0.60. Let me add one more weight and measure the thickness and length of the wire. That is 1.02, that is the thickness, and the length of the wire 0.61 now. Clicking on speedometer. Now, by clicking on table of readings, it will give you the readings of loading. It's time to unload the weight from the Young's modulus. After removing one weight, I'm clicking on speedometer to balance it. For each time, you can click on speedometer to balance the bubble. Now, the loading and unloading values are given over here, and the overall Y value is found out using the loading and unloading values. Let's move on to the next part of the simulation, that is stress strain curve. Here we are undergoing compression and elongation of the different materials to draw the force versus transverse displacement curve, that is stress versus strain curve. Here we have the compression machine and different materials: iron, steel, aluminium, copper and nickel. Let's check the compressibility of each of these materials by placing it in the machine. By clicking on this start button, which is there in the lower left bottom, you can click on this fast forward button to make the process faster. As it is compressing, it will automatically draw the graph on the projector. Next, steel. Clicking on start button and fast forward to make the process faster. Similarly, you can conduct the experiment with aluminium, copper and nickel. Let's go to the elongation part to find the stress versus strain curve. Here we are plotting the graph between force and elongation. Here we have tensile strength testing machine and iron, rubber, aluminium specimens are given over here. Let me start with iron. Clicking on the start button and fast forward button to make the process faster. You can see after a certain point of time, the rod breaks. Let's see for rubber. As you can see in the zoom in view, once it reaches the saturation point, it breaks. That is clearly given in the graph. Let's move on to copper. Now let's move on to the last part of the simulation, that is quiz, which will give you the analysis of how much students have understood the concept. Here we have set up 5 questions based on the concept in the simulation, and all 5 questions must be answered before hitting on the submit button. Once you click on submit button, It will give you the scores and it will also give you the check answer button to view which is right and which is wrong answer. You can click on explanation button to view the explanation of the question. Through these engaging experiments, you will gain a deep understanding of how metals behave under different stress conditions, whether it is tensile or shearing stress in the grain, elasticity through Young's modulus, or deformation through compression and elongation. You will see first and how the type of metal, the radius of the material, and the applied force all play critical roles in determining the behavior of metals. By exploring these concepts in an interactive lab, you will develop an intuitive understanding of the principles of elasticity, stress, and strain in high stress materials. So, let's dive in and test the limits of these metals. Thanks for watching.